Okay, we are continuing on. We got into chapter 16, I think, last time, and we started talking about some other thermodynamic sort of properties. And we started with entropy. And entropy, or the change in entropy, which is delta S, has to do with the amount of randomness disorder there is in a system. And as the amount of disorder increases, you also will see an increase in the entropy, and that usually will result in a positive value for delta S. And sort of opposite, as you create more order and the disorder decreases, the entropy will decrease and you will start to see a negative change in the delta S there. And one of the easiest ways to sort of look at disorder is phase changes, so solid, liquid, and gas. Obviously, solid is much more ordered and organized versus gas, which is much more disorder as everybody's flying around. So entropy is increasing as you go this way. And again, if we go from sort of liquid to gas, we would expect a more positive increase in our change in entropy. We're talking about thermodynamics here, and remember, thermodynamics oftentimes deals with the idea of reaction being spontaneous. And remember that when we're talking sort of about spontaneous in this sort of context, we're not really talking about the reaction necessarily happening very fast or anything about sort of the speed of a reaction. That is more kinetics. But what we are referring to here is under those conditions, whether or not this reaction should take place without any type of outside interference or outside help to allow it to actually take place. So as we kind of go through this chapter, we talk about reactions being spontaneous or, products being favored, for example. And sometimes people do refer to it more as products being favored rather than spontaneous. We were thinking about the idea of just under conditions, should this reaction take place, again, without any outside interference. And again, it could be a very fast spontaneous reaction. You could also have a very slow spontaneous reaction. If you leave it long enough, it will eventually occur. And again, that's what we're sort of talking about. Any questions on the map there? All right, so I think we did not do this one, right? This example here. I don't think we did. Maybe we did. Did we do this example? Anyone? No. We did? Okay. Thought it looked familiar. All right. So then I think this is where we laid up, if I'm not mistaken. So then entropy is also, like we saw in the previous chapter, it also is a state function. And as we talked about in the last chapter, state functions basically are only interested kind of in where you started and where you ended. So sort of your final and your initial states. And entropy, much like enthalpy, which is delta H, are state functions. And as we saw on that last chapter too, again, our sort of potential energy here, it doesn't really matter sort of the pathway you take to get to the top. What matters sort of where you end and where you start in terms of your change of potential energy. And again, as we talked a lot about in the previous chapter as well, when we think about chemical reactions, once again, our reactants to our products, again, our reactants is really kind of our starting stage and kind of our initial stage. And products are really our final stage. And as we saw with the change in enthalpy, the way that you could calculate the change in enthalpy is to take all the enthalpy values of your products, which is kind of your final state, minus the enthalpy values of your reactants. And as we will see here shortly for entropy, you could actually calculate entropy a similar way by taking all the entropy values of your products minus the entropy values of your reactants. Now, a couple of things is a little bit different with entropy, and here's a table of some entropy values that you could find. And like I said before, you'll usually find a delta H, a delta S, and a delta G table of thermodynamic values, usually in a book in a table towards the back. But one of the differences for entropy values is they typically are all positive values. In addition, Unlike enthalpy delta H, things in their standard state, you will actually have values for. So if you remember for delta H, things like O2 or just like a metal by itself will have a delta H value of 0 when you look it up in the table. Here you will actually, again, sort of see values. Just like the other tables that we talked about, you do want to make sure that whatever you're looking up is the correct thing and also the correct state. So you want to make sure, again, when you look it up in the table. A couple important unit sort of issues. Delta H, as we talked about, and we will see again in this chapter, typically delta H is in units of kilojoules, is sort of the units that are usually reported for a change in enthalpy value. When we talk about delta S, typically those are joules. So typically delta S is usually reported in terms of joules rather than kilojoules. Now, alone is not such an issue, but we will very shortly see a formula where both of those are used together. So you do want to be careful of units and not be off by a factor of 1,000 when you are using them together. So sometimes these guys do pop into sort of formulas together. Now, when we talk about entropy, that is the second law of thermodynamics. And the first law of thermodynamics is what we talked about sort of in the previous chapter, that energy can be converted from one form to another, but you can't create nor destroy it. The second law of thermodynamics is the entropy of the universe increases in a spontaneous process and is unchanged in an equilibrium process. So one of the ways that we can use entropy to help us make that sort of determination of whether or not a reaction is going to be spontaneous or not is to calculate something known as the delta S of the universe, or the entropy of the universe. And the entropy of the universe is made up basically of two things. It is made up of the entropy of the system plus the entropy of the surroundings. So if you calculate the delta S of the universe and you do end up with a positive number, that will tell you under those conditions, you would expect that reaction to be spontaneous and you would expect this reaction to basically occur. So if you end up with a positive delta S for the universe, it is going to be a spontaneous reaction. Obviously, the opposite is true, negative, really non-spontaneous there in that sort of situation. Now, again, if you happen to get an equilibrium process, you'll get a delta S of the universe that's equal to 0. And an equilibrium process, again, there's unchanged. There's not much change that's occurring because, as we know, in an equilibrium process, the rate of forward reaction and reverse reaction are equal to each other, which essentially just locks everybody into place. So there's not much change going on, right, in an equilibrium situation. And we get it equal to 0. So in order to use entropy to figure out whether or not something is spontaneous or reaction, you do have to actually calculate the universe, not just the system, not just the surroundings. You have to put them together and get that value and determine it. So then let's talk about how we could calculate each of those things. We could calculate the delta S of the system, and sometimes people will call this the delta S of the reaction because, again, in most cases, the reaction is the system that you're looking at. And basically, to calculate the delta S of the system, we pretty much calculate the exact same way as we do the delta H of a reaction. And that basically is to take the delta S of all your products and you minus it from the delta S of all your reactants. So just like we did with delta H, you have coefficients in the balanced equation. So you do have to multiply the coefficients by the values that you look up in the table. And again, you would look up these values in the table and add up all the delta S's for your products and then subtract it from all the delta S's of your reactants. Once again, this is our sort of state function here, right? Final minus basically initial in this situation. And that will give us our delta S of the system. So let's take a look at one here and see what you come up with. We are missing CO2. Do you have CO2 on your handout? Where'd it go? Maybe it's on this large by some chance. CO2. There it is. We'll go with 213.8. That will go. Go with 213.8 joules is the S of CO2. All right, so these are obviously values you can find from a table. So take a moment here and calculate the delta S of the. Okay, let's take a look at it. So once again, we're going to calculate this by taking our products minus reactants. Obviously, in a lot of cases, the numbers will not be given to you in the problem. You will usually have to refer to a table to look up all these values. So here our delta S here of our system going to be 2 times our value of CO2, which was 213.8 joules, where that's all of our products. We will then subtract it from all of our reactants. So we have 2 times our value of CO, which is 197.9, plus our other reactant, which is O2, and there's only one of them. So that basically is just 205 joules there. Again, just like we did with delta H, we do need to take those coefficients into account when we're doing it. And if we pop all that in there, we're looking at maybe a minus 173.2 joules in this case. First off, any questions on the calculation? Now, we did get a negative value here for our delta S, but once again, this is not the delta S that we could use to determine whether or not this reaction is spontaneous. But we can use it to sort of understand what is happening in terms of the actual reaction itself. So when we look at this reaction and we end up with a negative value of delta S, that means the disorder here is decreasing. The amount of order is also increasing, same thing basically. And we could figure that out or make an assumption without even necessarily doing the calculation in terms of what we would expect the sign to be for delta S of the system. Because if we look on our reactant side, we have 3 total gas molecules, 2 there and 1 there. When we look on our product side, we end up with only 2 gas molecules. So in this particular case, we got 3 things flying around crazily, and then we end up with only 2 things flying around crazily. So we actually increase the amount of order as we have less gas molecules flying around and moving around and causing disorder. And because of that, we would expect this reaction, or this system in this case, to see a decrease in the entropy and a negative value. And that's exactly what we got here, a negative value for our delta S of our system. So again, before you even do the calculation, you can kind of look at the reaction. And if you do end up on your product side, for example, with more gas molecules than you started with, that would increase the amount of disorder as you'd have more things flying around. And you would expect when you calculate, for example, the delta S of the system, that you should have a positive number in that case. So you can sometimes make a prediction, and that's a lot of questions. Sometimes you do come across in thermodynamics chapters. They oftentimes will not give you numbers or anything like that and just go, hey, you know, this thing's positive, this thing's negative, what do you think's happening? Are you increasing or decreasing and stuff like that? Any questions on that part of it there? So as we were just talking about there, you can make sort of a prediction when you look at an equation to sort of understand what is happening in terms of the reaction, increasing the order or decreasing the order. And again, as we just saw, if we end up with more gas molecules than we started with, we would again expect a more positive value. Like we had in that example, we ended up with less gas molecules than we started with, so we would expect a negative value. If there happens to be no change in terms of the gas molecules, then delta S may be positive or negative, but it probably will be a relatively small number, again, because you're not tremendously increasing the disorder or tremendously decreasing the disorder if you end up with the same number of gas molecules. So if we take a look at just this reaction here without doing a calculation, should we expect the delta S for this system to be positive, negative? What do we think? This one should be a delta S that is negative, yes. And we are increasing the order in this case. We are actually starting on this side with 1 gas molecule only, this guy, and we are ending on this guy with no gas molecules. So we have something flying around in your face to nothing flying around in your face. A lot more order has been created, again, decreasing the disorder, and we see a negative value for our delta S. Any questions on that there? Now, let's talk a little bit about the surroundings. So now that we understand how to calculate the delta S of the system, the other component that we've been talking about for the delta S of the universe is the surroundings. And let's talk a little bit about what's happening in the surroundings and how the type of reaction can play an effect or a role as to what is going on. So on the left-hand side here, we have a exothermic reaction happening here in the flask. And if you can imagine what's happening here, as the heat is being released by the flask from the system to the surroundings, that means that the surroundings is going to pick up all that energy that's coming off from the reaction in an exothermic reaction. That means all the surrounding molecules are going to start to move probably a lot faster, right? Because they have now more energy coming into them. And that's going to create a lot more disorder in the surroundings. So we would expect the delta S of the surroundings in this sort of exothermic situation to result in a more positive value for our surroundings entropy value as it's picking up that energy. If we look to the right there, that is an endothermic reaction. And that means that the system here is sucking out all of the energy from the surroundings. The result of that is the surrounding is going to lose a lot of energy. And if there's anybody moving around in the surroundings, that means they're going to kind of slow down a lot and not going to be moving as fast as they're losing all that energy. What that's going to do is for the surroundings in this situation, they're going to basically create a lot more order in this case because you don't have things flying around really fast. They're slowing down. They're not moving as fast, creating a lot more order. And that means in this situation, in an endothermic process, we would expect the delta S of the surroundings to be a more negative number as we're creating a lot more order in that situation. So there is a relationship to our sort of exothermic and endothermic processes and the delta S, or the entropy of the surroundings. Remember again that our delta H is a negative number when we're talking about an exothermic reaction, and our delta H is a positive number when we're talking about an endothermic reaction. So the delta S of the surroundings is proportional to negative delta H of the system or the reaction. So what does that mean? That means if we take a look at the delta H and our delta S of our surroundings, which is basically negative delta H of the reaction. So again, in an exothermic process, your delta H is going to be negative, and your delta S will be negative of that negative, which turns it into a positive value for your delta S of your surroundings, increasing the disorder. In an endothermic process, your delta H is going to be positive, and a negative of a positive is going to give you a negative value here. And again, that's going to give us a negative value for our surroundings. So it's sort of an opposite relationship. If energy is being released from the system to the surroundings, we would expect a increase in the amount of disorder in the surroundings, and vice versa. If the surroundings is sort of losing energy to the system in an endothermic process, we again would expect everything to become more ordered. Now, when we talk about this, the actual temperature of the surroundings can play an important role in terms of whether or not you're going to see this big sort of entropy change in the surroundings. So for example, if I had a surroundings that is very high in temperature, the actual entropy change that you see in an exothermic reaction may not be all that different in terms of the surroundings. So if you think about it, if you lit a match just on the outside here, you could put your hand next to it and you could feel the heat coming off, right, of it. But if you took that match and you had it burning in, like, say, an oven that's at like 600 degrees or 500 degrees, the little bit of heat that's coming off for the match is probably not all that big of a deal to the surrounding temperature, which is super hot to begin with, right? So if you're actually starting with, don't try any of that at home, by the way, if you are starting with a really high temperature in the surroundings, the extra energy coming from your exothermic reaction may not make all that big of a difference in the entropy because it's probably high to begin with because you have a lot of energy out there to begin with. Under lower conditions or normal temperatures, that exothermic reaction can provide a significant amount of change to the entropy under those kind of lower conditions. So how do we calculate sort of the surroundings, delta S of the surroundings? As I mentioned before, that temperature of, it's all over the place. That temperature of the surroundings does make a difference. Again, if it's high to begin with, you'll see a small change in entropy. If it's low, you'll see a bigger change. So to calculate the delta S of the surroundings, it is equal to minus delta H of the system or the reaction divided by the temperature in Kelvin. Yeah. Now, this is important to remember. This particular one here does have the negative for that relationship that we just talked about, the sort of opposite relationship that occurs here. I point that out because later in this chapter, we will rearrange an equation and we will end up with pretty much the same looking equation, except there's no negative on that one. So this one for the surroundings has that negative in there as part of the formula. Later on, we'll kind of see almost the same equation, but again, without the negative sign that's present. So this is how we calculate the delta S of the surroundings. We put that together with our delta S of the system, which again is our delta S of our products minus the delta S of our reactants. And we add those together, and these are the two components of how we get to the delta S of the universe, which again, if it ends up being a positive number, that universe value, it is a spontaneous reaction. And obviously, if it's a negative value, then it is not. Any questions on that there? All right, so why don't we try one here, and I'll move some of these delta S values up. Delta S for nitrogen, 192 joules. For H2, 131. And NH3, 193. All right, so for this reaction here, basically the formation of ammonia, the delta H of the reaction is minus 92.6 kilojoules. What is the delta S of the system and the surroundings? And is this reaction spontaneous at 25 degrees Celsius? So take a few moments, calculate those things, and determine whether or not we expect this reaction. All right, so see how you're looking or doing here. So we're looking for delta S of the system and the surroundings. We do have this reaction here, ammonia. We have a delta H not of minus 92.6 kilojoules per mole. By the way, when you see the little knot circle there, that usually means under sort of standard conditions, table type conditions. And usually what that means is everybody was at 1 atmosphere for the pressures. Everybody was 1 molar if they were doing something with concentrations. Technically, temperatures really not, but 25 degrees a lot of times is the temperature and those things. But really, those two things, the pressure and the concentrations, are 1 atmosphere, 1 molar each. So usually those are the kind of values you get from a table. So we'll start with our delta S of the system, which once again, we're just going to take the difference between our products and our reactants. So on our product side, we do have 2 of the NH3s, each at 193 joules here. We're then going to subtract it from our reactants where we have 1 nitrogen, which is 192. We're going to add it to our other reactant, which is 3 hydrogens. And again, we do see values for these things that we normally don't see for our, I just may leave it as joules, for our delta H. And if we do all that good stuff there, looks like maybe negative 199 joules is the delta S of the system or the reaction in this case. Any questions on that calculation there? By the way, we could have predicted the sign of that by looking at the equation. Once again, if we look at the equation, I got myself 4 gas molecules here, and I am ending with 2 gas molecules. So once again, we are decreasing the number of gas molecules, which means we're creating order, and we would expect our delta S, like we ended up with there, to be a negative number. So again, sometimes when you do the calculation, you just want to make sure it does sort of make sense. Any questions on that there? Obviously here, we are doing delta S of the surroundings. So our delta S of our surroundings is equal to minus delta H of the reaction divided by the temperature in Kelvin. So that's at 25 degrees. So we're at our 273 to that. Going to give us 298 Kelvin. And now we can put it in. So you can go negative 92.6. I'm going to multiply it by 1,000. And the reason I'm multiplying it by 1,000 is that's going to convert me from kilojoules to joules. And the reason I'm really doing that is this number is in joules. That way everybody's kind of in the same units in this case. And again, S's or entropy values typically are given in joules most of the time. So that's going to get me 92.6 times 1,000 divided by 298. That's going to get me about 311 joules as my delta S of my surroundings in this case. Also makes sense if you think about what's going on in this reaction. My delta H value here is negative, which means this reaction is exothermic. That means it's releasing energy to the surroundings. It is a normal low temperature of 25 degrees, which means the surrounding is picking up all that energy and going crazy, which means we should end up with a positive value for our delta S of our surroundings, which once again we did in this case. Any questions on that? Lastly, to answer the question of whether or not this reaction is going to be spontaneous or not, we do have to calculate our delta S of the universe. And now that we have both numbers, and also a reason why I converted that number into joules, because I knew I was going to add them together. That way I don't have any issues of 1 in kilojoules and 1 in joules. We're going to go negative 199 for our system, plus a 311 for our surroundings. That's going to yield us a delta S of the universe of about $1.12, I think. Yeah. And that is a positive value, which means this reaction is going to be spontaneous or non-spontaneous. Reaction is going to be spontaneous, as we have a positive value for our delta S of the universe. Any questions on any part of the calculation there? Also, a really good example of a spontaneous reaction that is a relatively slow reaction if you do not use a catalyst. So if you didn't use a catalyst on this, pretty slow reaction. And again, remember, when it is spontaneous, it has really nothing to do with how fast or slow. Again, what it means, as we talked about, just under those conditions, we would expect this reaction to occur. Could be fast, could be slow, but eventually, without any outside help, this reaction should occur. Yeah. Any questions on that there? All right. Then continuing on, let's talk a little bit about the third law of thermodynamics. The third law of thermodynamics is that the entropy of a perfect crystalline substance is going to be 0 with an absolute 0 of temperature. So if you have a perfect crystal, remember our Boltzmann equation, W is the microstates and the ways of doing it. If you could only get a perfect crystal in one way, that means the natural log of 1 will equal 0, and you will end up with an entropy value of 0. Again, as we go from different stages, as we talked about, we do see an increase in the entropy as we go from solid, obviously from solid to liquid to gas. We're seeing that increase in entropy, increase in disorder. One of the things that tie these together, as you may be familiar with or not, is the idea of phase changes. And as we go from, say, solid to liquid, or liquid back to solid, that occurs at the normal melting point or freezing point of a substance. For example, water, that is 0 degrees Celsius where that occurs. And at exactly 0 degrees Celsius, you actually have both phases happening at the same time. It's not until you get a little bit above 0 degrees Celsius, you fully transition to liquid water, or below that you are back into ice. Now, as you may remember or may not know, there is a certain amount of energy required just to do the phase change at 0 degrees. And that is what is known as the delta H of fusion. And that is the energy required basically just to change the substance at its normal melting point, freezing point from, say, solid to liquid or liquid back to solid. For example, for water, that is roughly 6.02 kilojoules per mole is the heat of fusion, or roughly 335 joules per gram is necessary to do that. Now, the amount of heat and energy needed to do that transition is the same regardless of which way you're going. If you're going from solid to liquid, it's going to take you 6.02 kilojoules per mole. If you're going liquid back to solid, it's going to take you 6.02 kilojoules per mole. The difference is the process that's occurring as you go from, say, solid to liquid versus liquid to solid is different. As you go from solid to liquid, that is an endothermic process, right? You got to put energy in to melt your ice to make it liquid. And that would mean that this would be a positive value of 6.02 kilojoules per mole. And as you go back from liquid to solid, you have to release the same amount of energy, and that would be negative 6.02 kilojoules per mole going in that direction. So again, the number's the same. Just depends sort of which way you're going as to what the sign would be. There's also a similar type of energy requirement as you go from liquid to gas or gas back to liquid. And that also occurs at the normal boiling point of a substance. So for example, water, that's 100 degrees Celsius where that occurs for water. And it's the same idea. It's not until you get above 100 degrees for water that you transition fully into gas state, or below 100 degrees that you kind of transition to the liquid state. There is an energy required just to do that transition at 0 degrees Celsius. That is the delta H of vaporization. And for example, for water, that is roughly 40.7 kilojoules per mole, or roughly 2260 joules per gram. Now, again, it's the same idea as you go from liquid to gas. That's an endothermic process, so it's going to be a positive value, like positive 40.7 kilojoules. And going from gas back to liquid, it's an exothermic process, so negative 40.7 kilojoules going in that direction. By the way, obviously, if you are not dealing with water, other substances will have other values for the heat of fusion, heat of vaporization, and they will also have other boiling point temperatures and melting point temperatures as well. So there won't be 0 and 100 for everything. Again, that's specific for water. So that is the energy requirement as you kind of change phases. And again, we're not changing temperature when we're doing this. It happens exact same temperature. Again, for water, 0 degrees, you're just changing it from one phase to the next. If you did change the temperature and something stayed in the same phase, when we talk about heat and energy, that is our specific heat equation that we talked about in the previous chapter. So specific heat equation is used when we keep it in the same phase, but we change the temperature. When we do phase transitions, it's a heat of fusion or a heat of vaporization sort of transition that occurs. Any questions on that there? All right, then let's talk about another sort of factor that we can use to help us determine whether or not a reaction is spontaneous or not. And dare I say, we get to use another letter of the alphabet, and that is delta G. And delta G is what is known as Gibbs Free Energy. And much like the name implies, it is energy available to do some type of work. And as we just saw there, we can use the delta S of the universe to help us determine whether or not a reaction is going to be spontaneous. But we could actually use our delta G value as well to determine whether or not a reaction is going to be spontaneous. So if you calculate the delta G of a reaction, and it is a negative number, it means the way the reaction is written will be a spontaneous reaction, and you would expect a reaction to proceed from reactants to products the way that it is written. If you calculate delta G and you end up with a positive value, then the way the reaction is written is going to be non-spontaneous. But if you were to reverse the reaction and flip it around, then the reaction would actually become spontaneous. And that is because, like we talked about with delta H, if you flip a reaction around, your products become your reactants become your products. So when you do products minus reactants, all you're doing is just changing the sign. So again, it will become spontaneous in the opposite direction. If you calculate delta G and it equals 0, you're at an equilibrium situation that occurs. We will see several different ways to calculate delta G, and the best piece of advice is, as we go through the chapter, is I would choose the way that is appropriate for the question, and what's given to you is the best way to kind of decide which way to do it. So let's take a look at one way that we could calculate delta G, and we could calculate delta G by taking the delta H of the reaction or the system minus T, which is our temperature in Kelvin, times the delta S of our system, our reaction. So go system on both of those if you want. Now, this is one of the equations that I was talking about earlier. This is an equation where we have delta H involved and delta S involved in the same equation. And as I mentioned earlier, typically delta H is kilojoules and delta S is joules. So you definitely want to be careful of those two different units. Your choice as to which way you want to convert it, but you usually need to convert them into one set of the same units, put them both in joules, and then at the end you can convert them back to kilojoules, your call, or you convert them to kilojoules as well. But you don't want to leave them like that. Otherwise, again, you're going to be off by that factor of 1,000. When you do that, you got to make sure they're in the same unit. So again, our temperature does need to be in Kelvin in this case as well. And we could definitely use this equation, obviously, if we are given a delta H value or a delta S value, or we calculate it, we can put it into this equation if we wanted to. Now, how can we also calculate delta G? Well, delta G is just like any of the other thermodynamic sort of properties that we saw before, and we can calculate delta G of the reaction by just the same way we do delta H and delta S. We take the delta G of all of our products, and we subtract it from the delta G of all of our reactants. So products minus reactants is another way that you can calculate delta G. You will typically look it up in a table along with your delta H, delta S values. These are typically, by the way, referred to as the delta G of formation, just like delta H, when you look it up in the table, is sometimes referred to as the delta H of formation. So that little F on the bottom is there. And like I said before, delta G is very similar to delta H in the fact that when you go to that table, much like delta H, for anything in its standard state, we'll have a value of 0. So if you have something like O2, N2, some type of metal by itself, uncombined, we'll have values of 0. So it is really only entropy S that if you go to that table, you'll find values for those guys. For H and G, you will find zeros for those things. As I mentioned earlier, those sort of standard state conditions is typically what that little knot means when you see it next to an H, an S, or a G. And usually that means that you're kind of calculating those things under standard conditions. And the typical standard conditions is kind of those two things I mentioned. If you're dealing with any type of pressure, the pressure needs to be 1 atmosphere for everybody. If you're dealing with any type of concentration like molarity, it needs to be 1 molar, and that's basically standard conditions. And if you ever look at a thermodynamic value table, typically in the back of your book or wherever you find it, typically those are the very common conditions that those are calculated from. 1 atmosphere for pressure, 1 molar for concentration, and usually they're a temperature of 25 degrees. It's kind of almost like a standard temperature is typically used for it. So those are two different ways that you can calculate the delta G. We'll see a couple more as we go through it. But as I mentioned earlier, the best piece of advice is just to kind of calculate based on what's given to you. So if you're straight up given a H and S value, put it into the previous equation. If you're pretty much just given the reaction, you're like asked to calculate the delta G, you should go find a table and do products minus reactants. You know, that's just the best way to kind of think about doing it. Any questions on that? All right, so why don't we try here? Let me put those delta G values up higher so it'll be easier to see. Delta G values from the table. For CO2 minus 394.4 kilojoules. For H2O, we'll use the value that's there, minus 237.2. For C6H6, 124.5. And for O2, big old zero there. All right. All right, so calculate the delta G for this reaction and determine whether or not this reaction is going to be spontaneous based on that. Okay, so let's take a look. So once again, if this is the only thing given to you is the equation, go find yourself a table and look up the values and do products minus reactants. So that is what we're going to do here. Delta G here of our reaction, going to take up all of our products. So we got 12 CO2, so we'll times it by the value there, minus 394.4. We will add it to our other product, which has 6 waters, minus 237.2. That basically takes care of all of our products. We're then going to subtract it from all of our reactants. That's going to be 2 times, looks like 124.5. 124.5. And a big 15 times 0, basically, here. And if we put all that in, it looks like maybe negative 6405 kilojoules in this particular case. First off, any questions on the calculation there? This reaction is going to be spontaneous because we ended up with a negative value here for our delta G. So again, you can use delta G there to determine that. Since our delta G is negative, we would expect this to be spontaneous. And obviously, we would expect it to be heading towards the products, obviously, in this sort of case here. Any questions on that one there? All right. Now, as I mentioned before, sometimes you'll come across a lot of problems in thermodynamics sort of chapters where they really won't give you values, but they'll give you something like, hey, this thing's positive, this thing's negative. What do you expect to happen? So if we take a look at that other delta G sort of formula that we saw there that had the delta H and the delta S in it, and we just sort of evaluate what's going on, and maybe I'll rewrite it here as well. G delta H minus T delta S, and then maybe we'll put one over here. Delta G is equal to delta H minus T delta S. Maybe we'll throw one over here, delta G. All right, so let's take a look at sort of what might be going on if we have certain situations occur. So the first sort of situation that occurs is we do have a delta H here that's endothermic, which means we will have a positive value for delta H. And in this box right here, we will have a positive value for delta S. And that means a couple of things in this case. We will end up with a negative delta G at high temperatures. So we need really high temperatures there, or high temperatures to do that. The reason for that is you got to remember, as we talked about in terms of units, when we look at sort of these terms here, this guy's at kilojoules, this guy's at joules. So this guy up here, it's got like a 1,000-fold jump on the guy to the end there, the delta S. So the only way for, in this situation, the back part of this to become larger than the front part is we would need a really high temperature. So if you have a positive delta H and a positive delta S, you would need a really high temperature for that reaction to become spontaneous. If you have a low temperature, most likely that reaction is going to not be spontaneous. You're going to end up with a positive value for delta G because at a low temperature, this back part cannot overtake the front part in terms of the value and stuff like that, and you'll end up with a positive number. If we go kind of to this box here, this is an exothermic process where delta H is going to be negative in this case. And our delta S here is still going to be positive. Now, in this particular case, because this guy is negative and this guy is positive, that means that no matter what you do, you're always going to get a negative value for delta G at any temperature. Because our temperature is absolute temperature, the lowest you could go is 0 Kelvin, right? So can't have a negative temperature value there. So you will always, at any temperature, have a spontaneous reaction. So that's a really good situation. Obviously, if you're looking for a spontaneous reaction to occur, you got a negative delta H, which means you got an exothermic reaction, and you're also increasing the amount of disorder that's happening in that situation. Any questions on that there? We come down here to this box. That again is going to be an endothermic process for our delta H. So our H is going to be positive. And in this case, we're going to decrease the entropy, which means our S is going to be negative. Now, in this situation, because our S is negative, along with the negative here, that's going to turn this whole back thing into a positive number. And you got a positive number in the front, which means no matter what you do in this situation, you're going to end up with a delta G that is positive at any temperature, which means this reaction will not be positive or not be spontaneous at any temperature. You're always going to hit a positive value. The only way you can make it is just to flip the reaction around, basically. Any questions on that one there? Now, our last situation would be this box here. And here we have an exothermic value for H, so our H would be negative. And we also have a negative value for our S. Just like before, that negative there is going to turn the back end here into a positive number. So in this particular case, at low temperatures, we're going to get a delta G that's going to be negative. Because at low temperatures, it will keep this positive number lower than the front number, and we will end up with a negative number. But if you had really high temperature, if you had a high temperature, that would be enough to pull this back number to be larger than the front number, and you will end up with a non-spontaneous process. So these are, again, very common questions that you're sometimes asked. And like I said, that's kind of the question. It's like, hey, H is positive, S is negative, under a like normal temperature, should this reaction be spontaneous or not? So again, you could also obviously put some numbers in if you wanted to, but this is the way you kind of want to think about it as you look at it. Any questions on any of those scenarios there? Yeah. Okay. Then let's talk about temperature and the role it plays in a reaction. So let's say we were looking at this decomposition reaction here of calcium carbonate into calcium oxide and some carbon dioxide. And let's say the delta H for this reaction here is 177.8 kilojoules, and the delta S, not here for this reaction, 160.5 joules. So the first thing we want to know is this reaction spontaneous at 25 degrees Celsius? So why don't you calculate the delta G and determine if it is or not. So take an H given to us, we have an S given to us, so don't reinvent the wheel. Take the equation that has both of those in it. So we'll take our equation here. Obviously here 25 degrees, going to add a 273 to convert that into Kelvin. And popping in our numbers here, we're going to take our delta H, which is 177.8. Once again, I'm going to multiply it by 1,000 to get myself into the same units as my S, and that's going to convert me into joules. Remember, you do need to do some type of conversion, otherwise you will have kilojoules on one and joules on the other, which is not a good combo. 160.5 joules in this case. And if I do that, 177.8 times 1,000 to convert to joules minus 298 times 160.5, that's going to get me, you just need to remember that when you do calculate it now, the units here are going to be joules. You can divide it by 1,000, and we'll call it 130 kilojoules. 130 kilojoules. So again, a reminder that delta H, delta G are typically in kilojoules. Delta S is typically in joules. So those, again, the common units for those guys. So we do end up with about 130 kilojoules of energy here, or free energy. And because our delta G here is positive, this reaction is non-spontaneous at 25 degrees Celsius, right? And that also is something that we would expect based on our conversation we just had, because in this particular case, we have a positive value for H, a positive value for S, and under low temperatures, our regular temperatures, that's not going to do it for us to get to a spontaneous reaction. Now, can we use this information to help us figure out maybe at what temperature this reaction would become spontaneous? And we actually can. So if we wanted to sort of figure out, well, I know 25 degrees is not going to really do it for me. I could use this same equation. My delta G is equal to delta H minus T delta S. And we know that we do need a negative value for delta G. So that happens on the other side there of 0. So we set delta G equal to 0. We get delta H minus T delta S. And if I bring everybody over to the other side, I get T delta S is equal to delta H dividing to the other side. I get the temperature is equal to delta H divided by delta S, which I happen to have actually both of those values given to me in this particular case. And if I put it in here, once again, my delta H, I'm going to go 177.8 times 1,000. So it is in joules to match the joules I got on the bottom there, 160.5. And that is 177.8 times 1,000. Converting it to joules there, 160.5 dividing by, we'll call it 1108 Kelvin, which if I subtract 273 to convert it back into Celsius, gives me 835 degrees Celsius. That number is the minimum temperature required for this reaction to become spontaneous. I would say, just like we talked about with a positive delta H and a positive delta S, you need a really high temperature for that to become spontaneous. I guess 835 degrees Celsius would qualify as a very hot temperature, right? Or a high temperature in that case. By the way, that is also what we see on the graph, hypothetically speaking. I do see it there. And this graph is the pressure of CO2 versus temperature in Celsius. In this reaction, the only gas present is CO2. So we will not have any pressure until we start to make some CO2, and we won't make some CO2 until we get to the right temperature. So you can see it's pretty much flatlined, the pressure, until you get to 835. And at that point, we do start to see, obviously, some pressure developing. You may be saying it looks like it starts to develop before 835, and you would be correct. But at 835, we have exactly, I scribbled on it, 1 atmosphere of pressure, which is standard pressure. So that gets you to the standard pressure at 835. So again, this equation obviously can be used like we did there on the left to determine whether or not a reaction is going to be spontaneous or not, and just calculate the delta G. But in some situations, you could actually rearrange this equation and figure out if a reaction is not spontaneous, at what temperature it actually would become spontaneous. Any questions on that there? All right, so once you calculate this one, for the following reaction, delta H is minus 1204 kilojoules, delta S is minus 216. At 25 degrees, is the reactants or products favored under standard conditions? Okay, so looking at this one again, we have an H and an S given to us, so we'll go with our H and S formula. Seems like good deal. And in this case, again, I'm going to convert my number into joules. And again, you can convert it into kilojoules if you want the other number. but you got to do some conversion. We're going to minus it by 298 Kelvin, which is our 25 degrees converted into Kelvin, and our negative 216.4 joules here. And looks like we're going to end up with a negative 1139512.8 joules, or negative 1140 kilojoules in this case. Well, any questions on that calculation? This reaction is going to favor our products, right, and be spontaneous, going to head towards the product side as we have a negative value for delta G. Once again, we would expect this to sort of happen. We have a negative value for delta H. We had a negative value for delta S. That once again turned this back part into a positive value. And again, the only way for it to be bigger than the negative value is we would need a really high temperature. And again, 25 degrees is not a really high temperature. So under those low temperatures, we do expect this reaction to be spontaneous because it should yield you a negative delta G, which it did. Any questions on that there? All right, wrap that up.